Welcome to qnawire.
For this problem, we want to determine what the average translational kinetic energy of a molecule of oxygen gas is in this 2-mole sample we have. Now, the first thing we need to remember is that oxygen is indeed a diatonic molecule in its gaseous form. So what that means is that our total kinetic energy is going to be broken up into the translational part and the rotational part, since we are not allowing for any vibrational kinetic energy here. And the translational contribution is 3/2 kBt. So this is all we're concerned with right here, is 3/2 kBt. Now, if we have the temperature, we will be able to calculate what this average translational kinetic energy is. Of course, we don't have the temperature, we have these other parameters over here. So what we're actually going to do is we're going to approximate this as an ideal gas to determine the temperature, and then we will calculate the kinetic translational energy from that. So if we recall, the ideal gas law states that PV is equal to nRT. We want to solve for the temperature, so we'll have PV over nR. We will need to convert from atmospheres to pascals for the pressure and from liters to meters cubed for the volume. So for the pressure, there are 1.01 times 10 to the 5th pascals in 1 atmosphere. So this is about 8 times 10 to the 5th pascals. And then for the volume, we should recall that 1 liter is equal to about 0.001 meters cubed over L, which is exactly equal to 0.005 meters cubed. So now, if we plug in our expression here for the temperature, or sorry, we could have done it this way where we substitute this expression into our expression here for the average translational kinetic energy, or we can just solve for the temperature first and then plug that value in. And if we calculate that temperature, it comes out to about 243 degrees Kelvin, which if we substitute into 3/2 kBt here, we end up with 5.04 times 10 to the minus 21st joules. So there you have it. By approximating oxygen as a monotonic molecule, we were able to determine what its average translational kinetic energy is per molecule.